Nice, good timing. A minute early, not too bad. All right, hello everyone. My name is Charles Modrich. I'm your instructor today. Some familiar faces, at least one or two on the roster. I assume that everyone's been through at least ELT110, is that right? And hopefully, any other PLC classes, anyone? Has anyone taken another PLC class? Excellent. Okay, so probably in another school or another institution, right? Because this one's just this PLC class, this one and the one before, right? Okay, cool. So today we're going to play a little bit of catch up just to make sure everyone's on the same page, we all understand the same concepts, and we can all move forward more or less as a group. We're not leaving anybody too far behind. But just to let you know, the way that this class typically goes is every day I'll take attendance. Attendance is not technically graded, although I am grading on participation. So, the more you show me that you're working on things and, cogs are turning in your head, the better. But for Tuesdays when we have lectures and Thursdays when we have lab, Thursdays is the graded portion, okay? Because on lectures like today, I'll be recording through the camera and I'll be making it available online. Okay, so if you're sick, or if you're unable to come in, or if you just want to review, make sure that you have good mastery over the content. I'll try to make those videos available to you, okay? But Thursday, lab attendance is required, so that one is definitely, graded, that you are there in the lab and present and working on things and submitting work, because the work in this lab can only be done here while I'm present. So if you have to make up work, or if you want to do like homework or anything, that kind of has to happen in class, or if you, talk to me about it and we schedule something. But ideally, you'll be here every Thursday, and we'll do each of the labs in turn and just knock them out and it won't be a problem. Any questions so far? I do mean Wednesday. Yes, I do mean Wednesday, thank you. So Monday and Wednesday is this class, yes. All right, so start things off. Connor, thank you. Unsiok, how do you pronounce that, sorry?
Say Evan if you want.
Sorry? Evan, nice to meet you. Michael, thank you. Alexander, thank you. Roman, thank you. Andrew, thank you. Dylan, thank you. Angel, not here. That's the other guy from my last class. Andrew, no Andrew. Quentin, thank you. Dominic, thank you, sir. All right, pleasure to meet all of you. I'm looking forward to working with you more and talking to you all over the next semester. I'm going to ask for questions a lot. Does anybody have any questions? And raise your hand. That's the time that it's not necessarily if you don't understand something, but if you just want to know a little bit more about something in particular. All the stuff that we're going to go over in this class is just kind of like the beginnings of what you can do with a PLC and industrial control in general. It's a big field, there's lots to know. So if you're curious about something, if something doesn't make sense, and I ask a question, please say, what's on your mind, and we'll go through it as a class. Yes?
Is class always going to be in here?
Yes, this will always be in this room, unless something crazy happens, but we're scheduled to be here, yeah. Syllabus is online. So if you guys see over here in course materials, this is pretty much like where the main content will be on Blackboard. So go into course materials, and then I'll have, as we go through the weeks, I'll have things categorized there. I'll have PowerPoint presentations, the lecture videos will be in here, labs as they go through, submissions, all that good stuff. So this is the place to be. And then of course we have the syllabus is inside of the first week for now, if you want to review that. We'll probably go over it just quickly because I want to talk about just one thing, which is the way that the class is weighted, just to put that out there. So labs are 30% of the grade. It's a big deal because we're working with our hands in this class, right? The point of having a PLC and being able to work with a PLC is actually being able to work with it. Book knowledge doesn't really help as much as being able to actually do the thing. ELT140?
Yeah.
All right, welcome.
Oh, okay. It says 116 on the
Yeah, no, they got it wrong. What's your name, sir?
Andrew.
Andrew, yes, I gotcha. You're in the right place. Attendance. All right. Okay, so just going over the syllabus. Like I said, hands-on labs are a big deal, so a big part of your grade. Quizzes will pretty much just be a midterm. Because the term is so short, it's only 8 weeks, I don't want to do like, a 20% weighted midterm or something. But I am going to do like a 8 or 10% weighted midterm just to check in, make sure you know the content, you're doing well. That's where that comes from. Pop quizzes sometimes, maybe, look out for those. Homework, this may or may not stay here. This is the first time this course is being taught at this institution. So the content is still being created. I have a resource for homework, but it's still being spun up. So I'm not sure if that will happen this semester or next semester. So we're going to play that by ear. In the case that we don't have homework, this grade will be absorbed into the other categories, just kind of doled out equally. Participation, obviously, that's, are you asking questions? Are you really trying on the lab, or are you just giving up and sitting on your hands and waiting for an answer? That's the kind of thing that I'm looking in the participation grade. Just, if you're at an 89%, this is kind of where I can bump you over if I see that effort on your behalf. Okay. Final exam, obviously a big chunk. I want to make sure that you guys actually know this and can pass my class. So it's a big deal. We will have plenty of review. The way that I teach this class is very review-based. I'll show you. The midterm will be much like the final exam, where you'll understand the content and the way that I'm going to test it. All the vocabulary terms, where the bar is and what you have to meet. And then the final exam should be practice at that point. It's not going to be like new content throwing you for a loop. It's things that you should have seen before and should have understood if you were indeed paying attention during the class, right? So hopefully no worries, no stress, none of that stuff. And one more point is that I have a mic on me, so don't be afraid of being caught on the camera or anything. It's really only recording at me and right here. Yes?
I just saw someone walk by that was also looking around.
Oh, you want to grab them? Sure. That might be Angel.
Somebody I knew, but not here.
Okay. All right, we're just missing one more person, but we'll see. Okay, so that's the gist of it. Like I said, this is up on Blackboard under week 1 if you want to see it and review it. Otherwise, it should be pretty straightforward, and I'll launch into it. All right, so again, this is going to be a review. I'm going to try to make it as entertaining as possible, given the circumstances, but the new content will probably come like next lecture, unless I surprise you with something that you don't already know. ELT, oh, this is the old lecture, sorry. 240 week 1, there we go. Okay, so might as well start with introducing the star of the show, which is the PLC that we're going to be using today. Okay, so PLC, obviously short for Programmable Logic Controller, is a black box that we can use to easily program reliable industrial scale tasks. Okay, so we're going to learn how to use this particular model. It's an educational model, but it's a stand-in for things that you guys will see in your professional lives. Okay, it uses the same coding languages, uses the same inputs and outputs. Really the only thing that'll be different is like the actual program you use and the branding, right? It might be Omron or Siemens or Honeywell or whatever. They all have their different PLCs, they're all their own systems, but what we're teaching you in this class will be foundational and should be shared no matter what manufacturer you go with. Okay, but so this particular one is made by the Arduino Corporation. An educational wing of it is trying to teach people like yourselves on how to use these things, because it's actually old technology. Much like the Arduino itself, the original platform, the 18 mega platform, this PLCs, were really in their heyday in the 70s and 80s when we desired a way to knock down large punch card machines into smaller form factors and have them easily usable in an industrial environment. Then we went through a strange kind of, once computers started becoming more accessible, microcontrollers started hitting the market, miniaturization started becoming big. PLCs are still around, they're still $1 billion industry, and there's still millions of them sold. But there was a bit of a educational gap for a little while, and this program, amongst, as well as the Arduino platform itself, is looking to kind of revitalize that. So it's a very modern interface, it's a relatively new program. It's actually in beta, I believe. trying to give you the best and the greatest that can be applicable to the real world. Not only is it a great PLC in that it has 4 relays that we can control, just like a typical PLC, as well as 8 inputs. It has various voltage ranges, Modbus, and can even talk Bluetooth and Wi-Fi. All right, so one thing that I'm really hoping that we'll get to later in this class is actually those IoT functionalities, where this box has enough smarts in it that it can talk over the internet. It can take data from a local sensor, or take actions to give to an actuator over the internet, over Bluetooth, over Wi-Fi, all of those things. Okay, our box is capable of talking those protocols, and we're going to see if we can play around with that later in the session. Also worth noting that there is excellent documentation and resources online. There's a whole online course that's completely free, open, and accessible, made by Arduino to be a companion with this device and with the simulators that we have here. So you guys might see in front of you in the boxes, and feel free to reach in there and root around. We also have simulators that come with these devices. Okay, these simulators. This one in my hand here is a switch simulator that simulates inputs, right? Whether something is high or low. And we also have another board that looks like this that we can use to simulate outputs, temperature control. So there's small heating elements on this that we can control with the relays, as well as a temperature sensor that we can control as well. Okay, so all of these were made by Arduino to be easily understood and worked with. So there's companion articles, there's videos, there's like entire data sheets on these modules, lots and lots of cool stuff that are available online with a simple Google. Again, worth mentioning that this is an Arduino Opta, O-P-T-A, Opta. That is like the keyword that you want to look up if you want to learn more about this stuff, okay? Just putting that out there too. All right, so this is where I kind of take a little bit more stock, learn more about you guys and who I'm dealing with. So one more time, how many people have used a PLC before? Awesome, okay. How many people kind of know what a PLC is? That's a little redundant. How many people think they know a good idea of how electricity works? Like you could explain the principles fundamentally. Excellent, okay. We'll revisit that just in case, but that's really good that we're all in that. How many people have programmed something before? Python, C, C++? Yeah? Okay. All right. Pretty good base. I think we're going to be a pretty cohesive group. Before I go on much further, we are dealing with electricity, so I have to say this. It is pretty much a risk that you have to be aware of. In this class, we don't really have any safety precautions. You don't have to wear eyeglasses. You don't have to wear gloves, although I'm certainly going to recommend that you do in like real life situations. The only thing that you can't do in here is bring drinks and food, pretty much. So please be aware of that. Water bottles, cans of Monster, stuff like that. Please keep it outside, or just don't bring it in. But we're going to go through some basic hazards. Just again, should be intuitive to you guys at this point, having gone through enough classes, but I'm just going to touch on it just in case. One thing that I make frequent use of in this class, going through some notation. Okay, we're going to be doing a lot of wiring diagrams in this class, and that involves doing lots of block diagrams, for example. Okay, so one common thing that I do is I'll explain, for example, how to hook up a PLC. Okay, so if you guys look in front of you at the PLCs that you have, we have plus, plus, and minus, minus, right in the upper left. Okay, that's the power going into the device, the input to the device. If you have a simulator attached to it, you'll have a little DC barrel jack input. Okay, that's where the power goes. It just goes into that DC barrel jack and then comes out over these bare wires to go back into the terminal again to power the PLC. Okay. That said, if you guys aren't familiar with this notation, this is called a net flag. Okay. If I have a power supply block over here, like it's a 12-volt power supply block, and I have a net flag here that says 12 volts, and then I have another symbol here, the ground symbol. Okay? It's as if this point that says 12 volts and this point was connected with an invisible wire. Okay, that's called a net flag. All right, so it would be equivalent if I drew this messy line over here, right? Same deal with ground. Anywhere that we draw a ground symbol, if I have another device over here that takes 12V, I would attach it to ground just like so, okay? So a ground symbol is definitely something that's good to get used to drawing and knowing about. Worth mentioning, again, things that you guys might not necessarily know, is that there's different kinds of grounds. For example, chassis ground is not necessarily the same thing as earth ground or a signal ground. Chassis grounds being devices that have metallic chassis to them, right? That somewhere within the device that terminates somewhere else, either directly to the earth ground, which again is the third prong on the wall that leads to a stake in the earth somewhere in the building, right? That directs energy into the ground and gives us our reference potential. Chassis ground may or may not connect to earth ground, for example, through one of these earthing wires in a safety critical application. Or signal ground is usually something kind of that's within the device. That's when you start to get into like RF electronics and analog electronics and things like that. But for this class, we're really just going to care about this symbol here, which they call earth ground, but that's kind of the generic ground symbol, which is again to mean that these 2 points are connected and these things are connected as well. You know, one thing always good to keep in mind is, especially for our PLCs or any systems that are talking to each other galvanically means metal contacting metal. Okay, galvanic contact. Okay, so if we have a PLC talking to a power supply that also may have a sensor, right? You must have all of those grounds connected, right? All of these have to have a ground and they all should be common to each other, touching each other through some means of wire, right? Small tangent there, but I just wanted to get that out of the way so you know what I'm talking about when I start to draw stuff on the board. Here's what I was talking about with that chassis ground. Again, some very useful information for you guys to know is the difference between class 2 and class 3 devices. That is to say, how they're insulated. Okay, this is the reason that we're going through this safety is that devices that have a plastic enclosure around it, say if this is a motor and that motor has a plastic clamshell around it, where no wiring, if it were to have a fault within that motor, you couldn't energize the outside of the casing, okay? That the casing itself is providing insulation against that fault. In another case, where you're working with some bigger machinery that might have, you know, a metal casing, like a large CNC machine or something, if there was a fault that caused, I don't know, like a surge in here or an arc, that could energize the outside of the case, if there wasn't a conductor to bring that energy away from the case, it would remain energized. It could potentially shock you. And then you become the path that it goes through instead. So the reason, again, just touching why we have 2-prong versus 3-prong, and why some devices are 2-prong and why some devices are 3-prong is usually that safety factor. Can we embed the cord inside of the machine and hide it with plastic? Or is there metal exposed and we have to make sure that metal is grounded so it goes into the earth instead of our people operating it? Another thing that's really good to know that people don't often realize is the safety criticality of whether or not you have wet skin, dry skin, where the contact is, where you're in contact with, where's the current going to go, the amount of damage, the amount of current that flows. All of these things are very dependent on the resistance of the path that the energy travels through you, right? Just like a series of resistances, right? Resistors that are adding up, so does components of your body. And all those different components have different resistances that help protect against current flowing through your body. Okay, if you grab something with a wet hand, that's only 1,000 ohms, right? So if we're talking 1,000 volts, that's 1 amp flowing through your hand. Okay, where the equivalent case, the same situation, but you had a dry hand, that's 100 times less current that's flowing through you, right? It might be the difference between your heart stopping or not, or getting 3rd-degree burns or 1st-degree burns. All this to say, just be aware of yourself and potential means of conducting electricity to and from yourself. And the reason why we have gloves and PPE in industry and in the real world is to bolster these stats. Right? If we have a rubber glove or a rubber boot or a helmet on, something high resistance in between the thing that we're contacting and the place where the electricity needs to go, we hugely cut down on the amount of amperage that flows, right? The amount of current that flows through your body. Current is actually flowing through our body all the time. When you step on one of those scales with the metal discs, it's actually sending current through you. That's how it works, and it measures the resulting amount of current that flows. The amount and the voltage that's flowing through you is really the thing that determines the level of shock and damage, right? The literal power in watts that's flowing through your body at a given time. One more thing is that not only does wet skin and dry skin matter, whether or not you pass the skin barrier matters, right? If you're working with relatively low voltage and you get stabbed by the copper that is energized, it passes your skin resistance and that turns to zero, right? So when we're talking about, maybe the only thing that's between you and the wet fleshy bits on your inside from getting vaporized is your relatively dry skin. When you get poked, it's not there anymore, right? So these are things to be aware of, that relatively safe situations can turn unsafe without PPE to guard you against. Okay. One more thing is that GFCIs, ground fault circuit interrupters, are fantastic devices, but they're not end-all, be-all, save-all, right? These are required to be in bathrooms because they turn off a lot more quickly than your typical circuit breaker. The amount of current that ultimately flows is much less, but it's not zero. It's still enough to stop a heart. It's still enough to cause damage. You can't really rely on these saving you. I'm just, again, putting that out there because people rely on these safety mechanisms thinking that, we've been doing this stuff for 50 years. This stuff is now inherently safe. It's not. It protects you and mitigates the damage, right? It's only on for 1/10 of a second or 100th of a second rather than, half of a second, but still more than nothing. Okay, so whenever you guys are dealing with these circuits or you aren't rated to be dealing with these circuits, right? We're not quite out of school yet. We're not quite electrical engineers or contractors or whatever we want to be. So until you're certified, please be safe and use professional services until you're ready and accredited. Okay. This is a very interesting chart. So again, it's the voltage and current that matters. The voltage ultimately determines how much current flows through you. So a high amount of voltage will, pass a relatively high amount of current for a moderate amount of resistance. But this is what we're actually talking about in terms of what does a milliamp do to the body? What does an amp do to the body? And it really is 1 milliamp starts to activate your nerves. Okay, raw, I guess you could say, free-flowing electrons, okay, can activate neuronal tissue, just like TENS devices, right, that you have the pads and then you can get shocked by it. It's the same thing. It's just electricity passing through your tissues that's messing with your musculature. At 10 to 20 milliamps, this is when things start to get scary because it starts to not only activate your pain sensors, but it starts to activate your muscles. So if you're clamped onto something, it will keep you on there to where you can't actually break hold. It will activate your muscles and make you clench harder than you ever could to release it and keep you there. So this is where things start to get really dangerous and really deadly when we get past this threshold because you can't let go. Or if you're tripped against something, you'll start to seize. You'll be unable to remove yourself from the situation. And 10 to 300 is this is where you start to cook, and here you're pretty much cooking like a hot dog. So, fun facts. This is my personal rule of thumb. I didn't really give you guys an intro. I apologize, I kind of just launched into it. Again, my name is Charles Modrich. I've been an electrical engineer for about 10 years. I went to school for biomedical engineering and then struck out on my own for freelance design, circuit board designing, firmware creation, all that good stuff. And I've worked on 3 or 4 dozen different gadgets and hardware projects of robotics and wireless designs and all kinds of stuff. So I've worked with a lot of different voltage domains, from the residential voltage that you guys are more used to, like the 120 VAC, down to 1.8 volt devices, mini microcontrollers. we're not working with crazy voltages in this class, right? Like it's not an industrial residential class where you might come into contact with 240V or something crazy, but we will be dealing with 9 to 12 volts. People won't really give these much heed because you can put 12 volts on your skin all day and nothing will happen. Okay, that's the car battery, you know, you can tap it and electricity will flow through you when that happens. If you put one hand on one terminal and one hand on the other terminal, you will actually conduct electricity. It'll just be in like the microamp to picoamp range, okay, that flows through you. But it's only dangerous if it sticks you, right? So what I was talking about before, if we pass the high resistance barrier of our skin and we start to get a low resistance, 12 volts can actually pass a decent amount of current through a low resistance resistor, right? It turns into a heater. So 5 to 9 volts is something that you can feel on your tongue, you know, dab it against the tongue for checking a 9 volt battery. 9 to 12 is dangerous if it sticks you, again, if you have a copper inside of you, or if you're passing electricity, high amounts of electricity, and you turn off the current. If you turn on a device or off a device that's high current, you can get something called an inductive spike, which actually drives the voltage up temporarily much higher than this. So that's kind of where the dangerous part comes on. Then 24 volts and above is potentially deadly. That's again where if you stick yourself, if you happen to have just a bad path to you, it can interrupt your rhythm, it can do bad stuff. So please be careful. In general, 5 to 9 volts, 5 is like USB, by the way. USB devices run at 5 volts. 9 volts is like motors, 9 to 12 is more motors, and 24 volts and above is, you know, just be respectful at that point and above, I would think. Again, these are all just, you know, please be aware, in this class we're working with things that can potentially harm you. We've already gone over all the other shocking things that can happen. We're not going to be working with soldering irons in this class, but components can get hot, right? We're working with heaters. If you short something for a while, that component can get really hot and potentially burn you. We might work with wire cutters when we're working with stripping wire and things like that. So again, just please be aware. Again, this is another PSA. Don't work with line level voltages in your house or otherwise unless you're rated to do so. If you have a certificate from an authoritative body that says, yes, you are not going to hurt yourself and others, you can do it. One more thing, lockout, tagout. Anyone know who lockout, tagout is? Cool, okay, great. So for the rest of you guys, if your workplace ever has a lockout, tagout system, if you are ever briefed by HR on this, pay special attention. I mention this is because people lose their jobs all the time because they don't pay attention to lockout, tagout systems. Something behind this lockout, tagout will kill you if you mess with it. It's typically how this goes. Okay, that there's something big and dangerous or shocking or sensitive or something, and they will fire you if you get past there without the proper authorization. Okay, so I mention this because this is another thing that you guys should be aware of and to treat with respect when you are actually in the industry or, you know, out and about in the real world. Just things to know. I think I'm gonna keep it there. Skip some of this. Gloves. We've already gone over gloves. Power tools, fasteners. Okay. All right, skipped through a lot of, oh, of course I knew it was going to do that. This was all content from the ELT110 book. I believe you guys have seen this before, but I'm just going through it again as just safety consciousness, right? Always good to go over. But don't need to know how to use a ladder. Don't need to know which gloves to use. Book stuff. Okay. All right. So now we're going to go back into some fundamentals. I know you guys all raised your hands, so I'm going to make this quick just to make sure we're all on the same page and we're all talking the same language. Okay. One thing that I'm going to keep doing in this class too is I'm going to keep harping on what I call the hydraulic analogy. Okay, so I've definitely brought this up before, Anyone know what the hydraulic analogy is? Ever heard of it? Oh, great. All right, that's going to be fun. I like it a lot. So when I think about circuits, electricity, when I'm running simulations in my head, what will this circuit do? How will it function? I run something called the hydraulic analogy. Okay, there's really cool, you can almost think of it like a metaphor or a simile. We can directly replace electric components with hydraulic ones. So a battery, as we know in real life, is a chemical reaction that creates free electrons within an electrolyte. Okay, so what this does is create voltage, right? It's a source of voltage or a source of electrical energy. The equivalent to this would be a pump in a hydraulic system generating pressure. Okay, so in this case, in the hydraulic analogy case, pressure relates to voltage, right? The harder we push on water, the more water will flow as a result. The more electromotive force we push on electrons with, the more electrons will flow as a result, which we define as current. Okay, same deal. In the hydraulic analogy, we have flow, and in electronics, we have current. Easy enough, right? Lastly, to complete Ohm's law, resistance is pretty much the same as resistance in both cases. Okay, in this case, the hydraulic analogy case, the metaphor is a pipe of reduced diameter. Okay, it would kind of be like two resistors in series. Okay, where this is, I don't know, like like 1 ohm, and this would be like 3 ohms. Okay, we can see that if we tried to push water in through this end or any other end, that this part of the pipe would offer about 3 times as much resistance to flow as this part of the pipe, right? Assuming that this is 3 times the diameter, or 1/3 smaller, right? So again, if we have a pump that's pumping with some pressure P or V, we have some ground potential, which is a waiting pool of water, right? It's pulling water up from this reference point, okay? The amount of energy in here, okay, you guys remember that voltage is a relative measurement, okay? It matters that we're measuring the difference between this pool and the top of this pump. Okay, so if this pool was on the top of a mountain or on the bottom of the ocean, the difference between this point and this point is still what we're defining as pressure. Okay, if this pool was on the bottom of a mountain, a mile down, then that would be quite a bit different voltage. Same deal with voltage is what I meant to say, which is that the voltage of one point and any other point is only a difference, okay, that we define. So we define that reference as ground, almost always, okay? The reference potential or the reference voltage. Here, ground is the potential energy of this pool of water. We are adding energy to that system by the use of a pump. Okay, so now we're at a slightly higher energy level or a higher voltage, and we can do things with this voltage or with this water now, right? We have some amount of energy in here, potential energy, stored in the height difference that we can use to do things with. We can move a pinwheel, and that pinwheel can do things to do work, right? So in the passive case, in our simple plain resistor case, that would be like putting this water into a basin that has this reduction, and then this is our flow. It's the same all the time, right? It's always flowing some amount of water through the system. This is our resistor, right? The resistance to flow. So the resistor in the hydraulic analogy is equivalent to just a straight pipe, right? Some passive resistance to movement. Okay, and we can do this exercise for other things too. We can do capacitors. Okay, capacitors in a hydraulic system look like fluid bladders. Okay, so if you imagine that this is a rubber bladder, okay, if we push on this side, some amount of flow is going to occur as water fills this basin, right? That's the capacitance filling up with electrons, or our bladder filling up with water. And as this pressurizes over time, the bladder will become more and more pressure, the current will become less and less, and eventually, at steady state, this will just be filled with water at some pressure. Are you guys with me so far? You over capacitors and stuff? Great, awesome. Is this cool and makes sense so far? Like, is this kind of making some connections here? I thought this was so cool when I first learned this, because I didn't understand like how capacitors and inductors and how current flows in response to voltage, and this just made it click for me. So whenever I see even advanced like Kirchhoff's laws, when you guys start to do that for like 210, ELT110, 210, this still all applies. It's still perfect. Even mathematically, you can rederive all of the more downstream equations and calculations using the literal equivalents for hydraulics. There's also like spring systems. You can do all of these analogies with springs and tethers and stuff, dampens. In any case, to complete the analogy, I'm going to go through inductors. So inductors, again, super cool for like learning what an inductor more or less does. An inductor in a hydraulic system is a pinwheel. It's a pinwheel. So as current flows through here, okay, if current starts flowing through here, we're going to build up inertia in this wheel, right? It's going to spin. It's at zero, it's not going to be spinning. If current comes in here, it's just going to start spinning slowly. It's not going to spin at first, but it'll spin slowly. At steady state, after it's been flowing for a long time, the water will more or less freely flow, right, with the pinwheel. It won't give much resistance. If it stops flowing for any reason, if there wasn't current coming in through here, this pinwheel would keep moving, right? It would have a little bit of inertia, it would still keep turning over, and in doing so, it would continue to flow water out of here, okay? So if we have a reduction in voltage here, the current doesn't stop flowing, okay? And the equivalent in here, of course, for the electrical situation is that we have current flowing through this wire. The current flowing through the wire, the solenoid, or whatever we have starts to create a magnetic field. It stores energy in the magnetic field, okay? During steady state, all of that energy is collected in here, and if we were to cut off the supply on this end, that field would start to collapse, right? It would collapse back down, which would create voltage in here and shove electrons back out. Pretty much a similar thing that we're storing energy, and then we're letting it go, okay? So I'm going to show you guys all that again in video form, but I love telling people about this just because we're not going to go through inductors and capacitors. Resistors are certainly helpful, but I'm telling you all of this because in a little bit I'm going to show you how to apply this to our PLC. Where our PLC, I can describe it as not something that switches electrons around, but I can show you as if it was powered by water. And I think that will make a little bit more intuitive sense. I'm actually going to launch into that first. Talking about it, I'm just going to do it. So the last couple times, I tried to tell people how to use a PLC. There was some confusion, especially with how to wire relays. That's a little confusing at first, but I think I'm just going to try to teach it this way and let me know if you guys find it a little bit more interesting. Get a little more board space too. Okay, so going forward with our hydraulic analogy, I'm going to describe the different things that the PLC does and how to connect to it in a slightly different way. Okay? So here we have plus, minus, minus. Here we have our I/O. As you guys already know, this is input only, right? So I2, I3, and so on. And then down here, we have our relays. All right, so the whole reason why I'm going through this exercise is to make you guys understand really how to work these relays more than anything. You guys have already worked with PLCs, so I'm trying to not labor on this point, but also make sure we're all like aligned. If I was going to draw, how do I attach a resistive heater to this device, right? How do I make a PLC that can turn a heater on and off with its relay? What do I do? How do I draw that? The way that I draw that is we have to first wire up the device, right? So we have to have, well, first we have to have a power supply. So I'm going to draw in my 12 volt PSU here. Draw my net flags to get that hooked up. It's 12 volts and ground just like that. In order to power the PLC, we have to have some power going into it to run our microcontrollers and things, right? Some small amount of current has to run the computer inside there, so we need to attach a power supply to our device to power it up. For this example, we're not doing anything with the inputs, we're just doing one output on a relay. Okay? Relays, as you guys know, but I'll tell you anyway, are essentially just an electromagnetic switch. Okay, in the olden days, they had guys on levers that were pulling levers to and fro depending on certain conditions, and well, people are expensive. They didn't want to pay those guys to do that for very long. So they wanted to get a box that did the same thing. When this thing happened, do this. Those early boxes used some things that had relays in them, electromagnetic switches that when you applied current to them would open and close two contacts, literally two pieces of metal that would flex away and close together. When they close together, you would complete the circuit and allow energy to flow, right? Electrons would conduct through, and when you didn't power it, it would break that connection and turn off whatever you were powering. Okay, so again, in the blase electronic situation, we have 12 volts here, we have our resistor, and we have ground. Okay, this is how I would ask you guys to draw a very similar wiring diagram. A problem that will come up often is I will give you guys a scenario, written or spoken. You are an engineer in a bread making factory working on a PLC that has gone bust and needs to do X, Y, and Z. Okay, I'm going to tell you to draw a wiring diagram of the PLC of all your components, A, B, C, and wire those together. And that's going to look a lot like this. So this is your first example on what that looks like and what I would expect from you guys in terms of that. Okay. In the hydraulic analogy, we can think of a relay very much like a switch for a hatch. Okay, so if we want to run a pinwheel, okay, this isn't our relay pinwheel, this is a pinwheel that's doing something, right? It's crushing something or it's doing some sort of work. Okay, this is the hydraulic analogy. This is terminal 1, T1, this is terminal 2, T2. Okay, this would be T1 over here, and this would be T2. Okay, the pipe between T1 and T2 is separated by this controllable flap here. This is our relay. Okay, relay 1. If relay 1 is off, it's in this position, right? It's closed. If it's on, it's here, okay, allowing water to flow. And then of course over here, the water would just flow out to ground. This would be our ground over here, okay? The reason that I'm mentioning this is so many people will do this and then call it a day. And then they will wonder why their thing doesn't work. Does anyone tell me why this doesn't work on relay 4? There's no power. There's nothing to flow through it. Okay, this is exactly what I was trying to get out of the way early, is to say that you could control this relay all day. You could turn it on and off and on and off and on and off. Nothing would happen because all you're doing is connecting and disconnecting, opening and closing this flap to nothing. Air will flow through here. You know, there's nothing. 0 volts will be put on here and not put on here. What you need is to apply a voltage to this other terminal, okay, which is again what I said here, which is to say you put water in this pipe, okay, which will actually allow your pinwheel or your thing that you're doing to work, okay? Anyone confused on what I just said? Does it make a lot of sense now why this wouldn't work when I revealed the answer? Yeah, that'll come up again. If it does, just, you know, think of this in your head. Why would this not work? Why would you take points off? Because doing this does nothing. Connecting this here does nothing. Only when we actually have a voltage on here, be it 12 volts or 24 volts or even 120 volts. That's why we have 4 separate outputs, by the way, because you can have a different voltage domain on each of these. They're all separate. You could control a 9-volt device or a 120-volt device or a 240-volt device. As long as it's within the spec of your relay, which is to say 240 volts on ours, you can control it. So anywhere between 0 volts and 250 volts can be controlled. Okay? So just want to make that clear. Any other questions? All right, I'm going to play some videos now. A lot of it will be going through what I just said, but relayed in a bit more math in the situation. And then this one I know will be interesting because it plays more into developing the mental model of how to kind of simulate electricity in your head and understanding intuitively what's going on within the wire when we apply voltage and see current flow as a result.
Electric circuits and the hydraulic analogy. Introduction: charge, voltage, and current. Electric circuits are very much like hydraulic systems. Here we have a hydraulic system, a pump pumping water through a pipe, and that is very much like the battery pushing charge through a wire. These are the hydraulic and electric quantities in units. The volume of water is like the charge in an electric circuit. The flow rate is liters per second in a hydraulic system, or coulombs per second in the electric system, or amps. Potential is pressure in kilopascals for a hydraulic system, or voltage in volts for an electric system. Energy is measured in joules in both cases, and power is in watts in both cases. Let's take a look at a hydraulic circuit. Here we have a reservoir of water sitting at 0 pressure. This is a pump that pressurizes the water to 300 kilopascals. The water flows through this fairly fat pipe, so there's very little pressure drop along this pipe until we reach this narrow point. When the water squirts through here and drops from 300 kilopascals to 0 pascals, now if the flow rate is 1 liter per second, then the resistance of this narrow point is 300 kilopascals per liter per second. That's the pressure drop divided by the flow rate. Here we have an electric circuit that's very similar. We start with charge that's at 0 volts in the ground. The battery draws the charge up through and pressurizes it, so to speak, to 1.5 volts. The charge flows through this wire. The wire is a good conductor, so there's very little voltage drop through the wire until we reach this resistor, which partially blocks the flow of charge. The charge drops to 0 volts. If the flow is 1 amp, then the resistance of this resistor is 1.5 volts per amp, 1.5 volts divided by 1 amp. And there's a special term for that, ohms. 1.5 ohms means 1.5 volts per amp. The power is the flow rate multiplied by the potential. In the case of a hydraulic system, power equals flow rate times pressure. In this example, we have a flow rate of 1 liter per second and a pressure change of 300 kilopascals equals 300 watts. So you have 300 watts of power, electric power going into this pump, and you have 300 watts of heat energy being dissipated by this narrow spot. Now, that's not very useful energy. We could hook up a water wheel to get some useful energy out of this. So 300 watts in, 300 watts out. Now, similarly, in the electric circuit, power equals current times voltage. Current is like the flow rate. Voltage is like the pressure. If we have a flow of 1 amp and a voltage change of 1.5 volts, we have a power of 1.5 watts. That means this battery is producing 1.5 watts of power, and this resistor is dissipating 1.5 watts as heat. Again, if you want to get something more useful out of this, you could hook up a DC motor and do some work, or a light bulb and produce some light. In summary then, charge, which is measured in coulombs, is like water volume in liters. Current, which is measured in amps, or coulombs per second, is like water flow rate in liters per second. Voltage, measured in volts, is like pressure measured in kilopascals. Power is the flow rate times the pressure in a hydraulic system, or current times voltage in an electronic system, and the units are watts in both cases. Electric circuits and the hydraulic analogy: force, energy, and power.
So there's definitely cool stuff that you can, like I said, continue to do with this, because all of this still holds, right? All of the power equations, energy equations, all of the things that flow down from Ohm's law still hold with the hydraulic analogy. And once you get into things like RC delay circuits, resonance, the interplay between capacitors and inductors, the ability to visualize this really helps your understanding, I think. So that's probably enough of that. We just have one more, two more, three more on Ohm's law. All right, this one I think you guys will be very interested in. Because even late in my career, I had no idea. Oh, okay. I don't know about you guys, but my intuition doesn't hold up when I have a circumstance like this. Okay, if we have an input here, and we have an input here. Sorry, hold on. Yes, sorry. Okay, if we were to tie off these two in two directions, where these meet in an open circuit and these meet in a closed circuit, which is to say that they're connected together. Okay, if we instantly apply a voltage here, so if we ground this one and apply a voltage here, what happens along the rest of the wire? How does that current flow, since we technically don't have a load, a place for it to go? Right, so this part is completely open. There's nothing connected on these two cables, but these sides are completely closed. So intuition tells us that this would short circuit, and we would have a huge amount of current flow and not quite much of anything else. And at least that's what my intuition said at first, right? So think in your heads, like what would happen in this situation, right? Like, what is the actual thing that's happening of the electrons invading that wire? And this guy sought to answer that question, is what happens? To do that, he built a huge rig, which is that he had this same situation where he kind of had like a Y, okay, where this part of the Y was open and this part of the Y was closed together, these two wires. And then he made it really long. He made it like a 1/4 mile long. So this, the difference between this point and these points, there's a lot of wire. Okay, it takes the electricity a long time to propagate through that wire, or the voltage rather, to propagate along that wire. The next thing that he did was he used many, many measurements. So he measured here, he ran the experiment where he connected the voltage, saw what happened, recorded all of that, and then he measured the same thing at this point, took an oscilloscope to it, saw the voltage rise and fall as he applied the voltage, and then here, and then here, and then here, all the way along this line. So effectively, he could see lots of different points along this line as it happened over time in like nanosecond scale resolution. So that's what he's going to show you here. He's going to re-explain some of that stuff so it'll make a little bit more sense, but I just wanted to lay the groundwork of what's happening here. So these are the individual segments where this would be like the open leg, this would be the closed leg, and this is where he would be, applying the voltage. And of course, this is his oscilloscope where he's actually reading in the information. So here's what happens.
A much more complicated model. So now we understand this first bit. When we send a pulse of voltage down the wire, at the ends of the branches, the electrons aren't moving yet. But everywhere this wave has been, electrons have started moving.
Oh, right. So, sorry. One critical piece of information is people who still understand mathematically what's going on, right? V equals IR, still sometimes don't quite get what voltage and what current are and why one relates to the other. One question I hear a lot is like, how does the wire know how much current flows based on the amount of voltage that you apply to it? This experiment is here to answer that, which is to say that it doesn't know, it simply reacts on as small a scale as possible. When we apply a voltage here, an electromotive force, a pressure, the flow inside of the pipe, the water, starts to move, but only at that spot that first feels it. Okay, another simulation for this is if we have a very long pipe and we have lots of marbles, lots of ball bearings in that pipe. If you pushed on this end, it would take a little bit of time for these balls to propagate down and start touching each other and grouping up and applying force. Okay? So the wire doesn't know how much current should flow. It sees a force. Okay, force is imposed on electrons, and those electrons move some amount accordingly, right? Those electrons move into more electrons, which continue to push, and then all of those get pushed down the line, slowly but surely. Okay.
At the edge of the wave, the electrons are either clumping up or spreading out. Now, when this pulse hits the fork, 3 things happen. Part of the wave reflects back, part of the wave continues into the connected branch, and part of the wave continues into the disconnected branch. These waves continue until they...
So we just saw something very interesting happen here. Do you guys see how this bounced way up when it hit the end of that? That is, in essence, an inductive spike. Okay, that this is also what a wave reflection is. Have you guys ever heard of an RF reflection? No? Okay, that's probably a little bit too high, but the reason why we tune antennas, have you ever heard antenna tuning? Is so that the most energy comes out of that antenna as possible. What happens if you don't properly tune the antenna is that this happens. It bounces back. This is energy that's traveling, that's being reflected back into the system. It's not going out into electromagnetic energy, it's going back into the system.
Stopping all motion. And in the other branch, the wave reflects back low, actually accelerating the electrons in the wire further. This branching circuit is a dramatically more complicated system than the single cable terminated in a resistor, but hopefully you can see the same patterns in both. we can continue tracing individual reflections and waves and interactions between electrons in all of these wires and carefully predicting what will happen next. Or we can just fast forward to the end and see that all of this hardly matters, because after a few hundred nanoseconds, everything settles out and we get exactly what we expect.
So just like you said, this is what we expect, what our intuition told us at first, which is that when we apply a voltage to something that has wires that are shorted together, we're going to see that as a short, right? As we're close to our supply voltage, right? When we're on this side of the resistor, if we were to take a voltage probe, a voltmeter probe or whatever, and see what is the voltage on this side of the resistor, we would see high voltage, and on this side of the resistor, we would see low voltage in steady state, right? The energy, the voltage is dropped by that resistor, okay? But this is more or less how electricity works, which is, again, to say that when we apply voltage here, it steps through the system. This electron pushes this electron, pushes this electron, and so on. And these happen at really, really fast rates. So this is why most of your education is centered on like the steady state of things. It's after this system has been sitting a while, what is it looking like, right? Rather than the dynamics of that system when we're turning things on and off and doing crazy things like that. I'm not going to test you on this. The reason that I give you this is wholly for the benefit of your intuition, okay? To tell you, peel back the curtain just a little bit and go, what you know might be not exactly right. That there's always a little bit more to learn and understand about the reality of the situation. Yeah, so I highly, highly recommend you guys look up more videos on the hydraulic model, hydraulic analogy. This guy's video is awesome. He has several more, Alpha Phoenix on YouTube. All of these videos are also embedded in the presentation. Okay, so if you go here, you click on the YouTube channel, crawl through their channels, that's your homework for today. So watch some YouTube, okay? Not too bad, I hope. All right, this will be our last pair of videos. So we're going to go through one more quick, like 3-minute mathematical one, again, just for the benefit of your education. And then we will show the pair. It's Alpha Phoenix again, where he's going to show us how Ohm's law works, how current flows as a result of a difference in energy, or a difference in potential, rather. And then we'll go on to a few more just small short form videos, again, kind of rounding things out, telling you guys how the internals of things work, how does a transistor work, how does a relay work, all that good stuff.
Electric circuits and the hydraulic analogy, resistor behavior. A resistor partially blocks flow. When there is flow through a resistor, there is a drop in voltage or pressure in the direction of flow. Drop in voltage for an electric transistor, drop in pressure for a hydraulic resistor. Ohm's law says the voltage drop is equal to the current times the resistance. It's important to understand voltage drop means the difference in voltage from one end to the other. For example, if you have 10 volts here, 9 volts here, that's a drop of 1 volt. This resistor has a resistance of 1 ohm, or 1 volt per amp. If there's no current flowing through it, there's no voltage drop. If 1 amp flows through it, there's 1 volt drop. If there are 2 amps flowing through, there's 2 volts drop. Let's say that this hydraulic resistor has a resistance of 100 kilopascals per meter per second. If there's no flow through the resistor, there is no pressure difference. If there's 1 liter per second flowing through, there's a 100 kilopascal drop. And if 2 liters per second are flowing through, there is a 200 kilopascal drop. Energy is converted to heat. The power is equal to the voltage drop multiplied by the current. For this resistor, if the voltage drop is 1 volt and the current is 1 amp, the power dissipated is 1 watt. For this hydraulic resistor, if the resistance is 100 kilopascals per meter per second, if the pressure drop is 100 kilopascals and the flow rate is 1 liter per second, the power dissipation is 100 watts. These are the electric and hydraulic quantities in units. Current is like flow rate, voltage is like pressure, resistance in ohms, which means volts per amp, is like hydraulic kilopascals per liter per second. The power is in watts for both cases, volt amps in the electric case and kilopascal liters per second in the hydraulic case. The behavior of resistors is fairly straightforward, but the hydraulic analogy for capacitors and inductors is more challenging and more interesting.
All right. So the companion to that is showing that the hydraulic analogy, if you were try to rebuild it, oh, right. So the other reason why this video is great is it goes the next step down in showing you guys, or demonstrating rather, literally how electrons who are floating in a free electron cloud or floating within the matrix of a metal, which is to say a wire, works. Okay? When we apply a potential, we apply a force to one end. How do the electrons respond? How do we define voltage in the way we do and why? All of that is explained in this video. It's pretty cool.
Imagine that we had a wire made of positively charged atomic nuclei surrounded by a sea of negatively charged mobile electrons. A 1 meter long wire like this one has about 5,000 coulombs worth of free mobile electrons in it. So if we take 1/5,000th of the free electrons that are in a wire and we start to push them towards one side of the wire, they're going to build up and they're going to form a hill. Now, if we push until that hill is exactly 1 volt tall, we will have used 1 joule of energy to build that hill. That's one of the ways that you can define a volt. It's sort of the pressure that you achieve after using 1 joule of energy to compress 1 coulomb of charge. Now, if we look at this hill that we've built, the hill's made of electrons, which means that the top of the hill has electrons that are on top of a hill. Also, at the other end of the wire, we've depleted the wire of electrons just a tiny little bit. So the wire, being made of positive charges, now doesn't have enough to cancel those out. So we end up storing energy at both ends of the wire. We're storing energy over here because we've got too many negative charges that are too close together, and we were storing energy over here because we've got too many positive charges that are too close together. The more we compress the electrons at one end of the wire, the larger the difference in electron potential we've created, and the larger the Coulomb force is pushing any individual electron away from the concentrated bit towards the unconcentrated bit, and the faster they will push through any resistance. Now when we let go, when we release all of these electrons, all of the energy that we've stored in the field over here, and all of the energy that we've stored in the field over here, gets transformed into the kinetic energy of the electrons as they shoot down the wire trying to spread out. In actuality, they bounce around and end up dumping all of this energy into the metal as heat. But in the end, they will slosh back and forth until they have equilibrated their potential everywhere. The height of this hill, the voltage, the electrostatic potential is going to be flat when these electrons are done. And now we get to why the hydraulic analogy is so awesome, because that's exactly what's happening here. In a way, this trough of water is an analog computer, showing us a live plot of electron concentration in a wire versus distance, or at least a very good model of it. If you jam a bunch of electrons together, they store potential energy by crunching their electrostatic fields together. Just like when water molecules at high pressure, for example, at the bottom of this trough, get jammed closer together. Water isn't actually incompressible. Molecules do get slightly closer together, and they're slightly closer together over here than over here, until you let it spread out. I know it's not as pretty as the water models over on Practical Engineering, but I hope that it still gets the point across. The water trough is like the wire offering some resistance to flow. The water is like the mobile electrons that don't like to be compressed by voltage. And the pump over here on the floor is pumping a fixed volume of water per second, just like a constant current power supply. So let's recreate the experiment from the intro, where we ran a current through a wire. When the wire was connected directly across the supply, we got a smooth decrease in voltage from one end to the other. If I just turn on the pump and start moving water through the channel, we see the height of the water builds on one side. The voltage, potential energy of the water, drops as you go from one end to the other, and then the water is at a lower potential before being pumped back to the top. In this case, the potential energy is gravitational potential energy. This water is farther from the core of Earth than this water, but all the logic about water not wanting to be compressed works exactly for electrons if you're imagining one-dimensional current flowing down a wire. In the circuit, when I added an impediment to electron flow, a small resistor, the voltage in the same wire was pretty flat, but then stepped down and then was pretty flat again. If we recreate this in the water model by adding an impediment to flow, like this random piece of metal I found in the garage, we see that it obeys the exact same trend. The water level is flat, then it steps, then it's flat again. I hope that the water makes this intuitive for you. It certainly helps me. With the water, you just put a stopper in the way of the flow. So it's like, of course the water pools up behind the stopper. I like to think about electrons in the exact same way. This animation I showed in my last electricity video is probably my favorite animation I've ever made for the channel, for being an extremely direct picture in my head to video animation conversion. And we can see this principle at work. A battery pumps electrons around a loop of wire. Literally pumping one electron at a time with a chemical reaction is all a battery does. And those electrons the battery's pumping will then try to spread out and equilibrate everywhere through the wire, just like the water in the trough is trying to all reach the same height. If we make the resistor more or less resistive, or add more resistors, making a voltage divider of sorts, this is the sort of thing that you normally have to do math for. But in this case, the water height just responds accordingly, and it all ends up obeying Ohm's law, with the height of the water on both sides of each resistor being equal to the amount of water that's flowing through all of them, times some term that represents the resistance of each of these bits of metal that I'm shoving into the water channel to slow down the flow. It's also important to keep in mind that voltages are always relative in circuits, and the water model is no different. In the intro example, I had the negative clip of the multimeter attached to one side of the power supply for every measurement. A voltmeter like this only measures the difference in voltage between two leads. So when I say this point is at 1 volt, I really mean the potential at this point is 1 volt higher than the potential at this point. And when I say the potential here is about 0 volts, I really mean that this point and this point are at approximately the same potential. If you somehow charge this entire wire and the absolute voltage was way up here, it just doesn't matter.
So this is what I was talking about when I was talking about this system, right? Whether this is on top of a mountain or at the bottom of the sea, the potential difference between here and here is the same. It's just the relative between those two.
The electrons can't leave the wire. All they care about is the height of the hill they can see. In the water model, if you want to use height as a voltage equivalent, you need to choose a reference location. If I choose this as a reference point, we could say this whole area is at 0 height, and this area is at 2 centimeters height. Or we could drop a reference on the other side, and this area is at 0 height, and this area is at -2 centimeters height. The absolute position really doesn't matter. When you want to look at the voltage drop across a certain component, you only need to look at the difference in potential on both sides of that component. As an example, when you put a bunch of resistors in series like this, it's called a resistive divider, because it takes the total voltage drop across the entire circuit and divides it into chunks based on the relative strength of each resistor. If you tried to figure out what was going to happen in this situation using math, arithmetically with Ohm's law, what you'd end up calculating is the difference in potential, the difference in voltage on both sides of each of these resistors. In practice, this is normally known as the voltage drop across any given component.
All right.
In the plain wire versus wire with resistors.
So that's all I wanted to show for that. Again, this guy has great content, highly suggest looking him up. And hopefully that has taught you guys a little bit more, aided your intuition a little bit, so you can improve your mental model and what you see and think. We have a decent amount more to go. We've got an hour to go, but I want to take a small break. I want to take a 5-minute break. It's been a lot of things so far. Go ahead and go to the bathroom, take a drink, do what you want to do. We'll be back at 4:50. Okay. I'll get a drink of water. All right, so getting back into it, we're going to go through a few more electronic components that are relevant to the course. We don't use MOSFETs and transistors in this class directly. You know, obviously a PLC has transistors and MOSFETs within it that help with the functionality of things. But I feel like this is useful information to know, so I'm going to give it to you in short form. Here we go.
This is a transistor, arguably the greatest invention. They power pretty much all modern electronics. They act as switches and amplifiers, but use electronic control instead of physical switches. This type is called a BJT, or a bipolar junction transistor. This is the base, and the two junctions, the emitter and the collector. This tiny speck is the semiconductor, which makes the transistor work. Let's take a closer look. It's made of 3 layers, an N, P, and N-type. The P-type base lacks electrons and has holes. The N-types have spare electrons, filling the holes. This area now lacks free charges, creating a repelling barrier called the depletion region. When we apply a small voltage to the base, it reduces the depletion region, allowing electrons to flow from emitter to collector. Electrons want to flow from the battery to the LED. It's blocked until we apply a small voltage to the base, completing the larger circuit. And that's the basics of transistors. This is a MOSFET. They're arguably the most versatile transistor, so you gotta know how they work. Unlike other transistors, they can switch electronic signals faster and can be controlled with virtually no current. The MOSFET has 3 terminals: the gate, drain, and source. Each terminal is connected to a region on the semiconductor, which is where the switching happens. Let's take a closer look. This semiconductor has 2 N-type regions within a P-type body. The N-type has extra electrons, while the P-type has vacant spaces known as holes. Drain and source are connected to the N-type regions, and the gate is below the P-type, but is insulated by a metal oxide layer. When a voltage is applied to the gate, it creates an electric field that attracts electrons and repels holes away from this area. There's now a channel for electrons between the source and drain. This potentiometer controls the MOSFET's gate voltage, which changes current flow in the motor, and that's an easy speed controller. Comment what component you want to see next.
So the interesting thing about this is essentially showing you, how do we do solid state switches, which is to say, how do we turn electricity on and off without actually moving things? And that's how we do that. The reason that we don't use relays very often, solid state control, like MOSFETs or BJTs in industry, is reliability and just the voltage that's involved. So MOSFETs and BJTs typically can only really switch voltages up to like 30 or 60 or 100 volts. 120 volts, 240 volts, line level AC, not DC voltages is not something that you typically want to do with a transistor. You would want a solid state relay for that. However, relays, being that they really are the only electrically active part of a relay that's actually involved in your circuit, is the strip of metal that parts and comes together. Okay, that strip of metal is very thick. It can give large amounts of energy, up to 10 amps at 240 volts in many cases. But it doesn't really mess with the path, right? It's just a low resistance means for it to go through. It doesn't heat up very much. It has to click on and off. It can't be turned half on, for example. Those are a few downsides to it. But the upside is that you can control AC voltages, you can control large voltages, and you don't have to worry about, for example, MOSFETs and transistors have to contain all of the heat that they move. So if it moves 1 amp of current, it'll be like it's heating up with 1 amp, like a 1 watt heater. Okay, that package, that transistor will heat up when it's moving that current. Our relay, because it's only just a strip of metal, the resistance is very, very, very low. It doesn't heat up. It just switches and unswitches as it goes. But MOSFETs, like you saw with that simple speed controller, are nice because you can put a proportional voltage on them. It's not just full on, full off. You can be half on, a quarter on, quarter off. You can pulse it very, very quickly using techniques like PWM, pulse width modulation. Lots of fun stuff like that. But for our purposes in this class, we're really only working with relays. Relays, all they are, and you'll see this in a video, is again an electromagnetic switch. So there's literally a magnet inside of there, a coil, a solenoid, that when it's activated draws down a little flap. When that flap pulls down, it pushes a lever that brings those contacts apart and together. That's really all it is. And we'll see a delidded one on the left here.
This is a relay. It is an electrically operated switch that allows us to control high power device using a low power device. But how does it work? Well, it consists of two contacts whose motion is controlled by a small electromagnetic coil inside it. When this coil is powered, it becomes magnetized and both contacts make contact, thus completing the circuit.
So here's where you can see the rating of it. It's a little blurry, so you can't really see it very well, but it says 30 VDC or 250 VAC. Okay, so this is the rating of this particular relay. PLCs and other things, devices with relays in them will have their own ratings, but this is how we can tell the rating of this device. So we can power things that are up to 240, 220 VAC, or power things up to 30 VDC. If you go above that, it'll start sparking, right? This board or this device is only meant to withstand, I guess that just completely died on me, is meant to withstand a breakdown voltage. If you guys don't know what a breakdown voltage is, if we have two traces on a board that are running alongside each other, right, that have this distance, given sufficiently high voltage across these two terminals, there will be some voltage V that the air will break down and we'll get an arc, right? That the resistance, this resistance here, is overcome and we get an arc, current flows between these two traces. That's why we have our rating. So 220V rather than like 500V, if we did 500 on here, it wouldn't stay contained within this trace, right? Ideally, this would only flow over here when our relay turned on, right? But instead, it would jump over on its own. It would conduct just like a Jacob's ladder, right? The Jacob's ladder is this guy, the V, that you know, it kind of makes a zapping sound and it goes. You guys ever seen that one? Maybe not. I hope I'm not coming off crazy. Jacob's ladder. Electricity. There we go. It's this guy. Right, so this is showing arcing through the air, the breakdown voltage, that there's a very, very high voltage in between these two wires that causes the air to break down. Air has a resistance just like our skin does, right? That if we have a sufficiently high voltage, current will flow through the air and conduct electricity. One more thing, another thing that's different and that people often get confused is that when we have a MOSFET, okay, if we have a MOSFET that usually kind of looks like this, has 3 leads. When we give this guy power, you know, say if it's a P channel MOSFET, so this would be the gate and this would be like out. It's pretty similar to a relay where we have the voltage that we want to switch on one leg. We have our control pin, which if we put a high voltage, a logic level high voltage on this, whether that's 3 volts or 5 volts or whatever our logic is, this will cause the switch to connect these two sections or not. And then the interesting thing about a MOSFET is if this is only, you know, like halfway up, this will only conduct halfway. It'll be like the resistance is higher. Okay. All right. Take a moment for questions. Any questions about anything we've gone over so far? Anyone lost? We're all more or less on the same page? Great. Awesome. Okay, so I took this presentation from my PLC ELT140 class, the one-level version of this class, so I'm not going to go over the history again, because presumably you guys already gotten that. The quick and dirty of it is, again, back when computers were first becoming a thing, they had a need for a generic computer, right, a black box that they could easily program and give to a guy without much education to use it in a factory somewhere, where you have an input A that you wire into your device to affect an output in some way. Turn a heater on, move a robot arm to some place, count the number of objects that are coming down, right? Simple tasks that they had to wire together relay logic for. So I'm not going to belabor this point too much, but one thing that you guys should know is those two connectors I was talking about. Okay, remember, our relay is just these two contacts, right? And whether or not these two contacts come together. Okay. Off-the-shelf relays actually have usually another terminal. Okay, they have this main terminal, which is called common, C-O-M. And then they have two other ones. There's the normally open contact and the normally closed contact. Okay, so NC, normally closed, NO, normally open, and COM is common. Okay, so the way that this works in a relay is that when we turn it on, right, there's another pin over here that when we drive that high, the relay will click on. Okay, and if its default state, our relay that we're using with our PLC is said to be normally open always, and that's like its only state. We just have one input, one output. Here we have one input and two outputs. Okay, we can choose to wire either to the normally closed terminal, which by default is attached to common, or the normally open terminal, which by default is not attached to common. When this activates, it's like this shifts over. So when we apply power to our relay, normally closed becomes open when we apply power to it, and normally open becomes closed. Okay, very, very important. So the really cool thing though, is that just through these common, NC, and NO, COM, and NC connections, if you had a bunch of relays that were just like this, that all had these connections to them, you could create simple logic, simple programs by wiring one input into another output and creating a wiring diagram that accomplishes at the speed of physics what you want to happen. Okay? So some guy had to sit down and he had to say, okay, we need 36 relays in order to implement this program and, you know, do what we need to do to take all of our inputs, do the math on them, and then write to the outputs. And then that math would be done by the wires in the relays that attach one thing to another so it is as it should be for a current state, right? That's crazy expensive and annoying and slow, right? It takes years to do anything. Pinball machines are massively complex. So there was a need to create a generic version of that. How do we make a black box that does this without having to, you know, wire 40 different relays together? That then eventually became a device that looks a lot like this, the Modicon, powered by punch cards the size of a small room, all that jazz. And then they became sufficiently smaller and smaller over time. Right around 1980, it really took off with Siemens, Mitsubishi, Omron, General Electric, and etc. Getting into the game, each of them making their own version of it. Okay, so around the class, oh, here it is. I'm going to borrow this, excuse me. Ooh. There we go, okay. Yeah, I'll just take that one, thanks. Okay, so this is one such device made by Omron. This is probably from the 90s, I would guess. But this is when PLCs really started to take off, right? Computers started to get into the game. Punch cards turned into terminals, turned into like early Windows and Mac OSs, and UIs started to get into the game, right? Where we started creating actual programming languages that involves the computer and compilation and code and all that good stuff. So fast forward to today, PLCs and related controllers are a $10 billion industry. Okay, again, this $10 billion industry has been running for the past 50 years, right, since the 1970s. Things are starting to get old, things are starting to get defunct, need replacement and upgrading, and hopefully that's why you guys are here in this class learning about this stuff, is because it's still relevant. There's still millions of these devices in factories all over the world that need to be replaced and maintained and all that good stuff, okay? So, as we've described already, wiring things together in order to create programs is slow and annoying. So we have IDEs, integrated development environments. Okay, where we can drag and drop and click together symbols that might stand for one or more relays, or any number of relay logic chains, and we can change them at the click of a button. It's pretty nice. PLCs can control any number of things because of the connectivity that we now have. For example, one thing that we're going to be learning in this class is Modbus, which is PLC to PLC communication. Okay, system architecture starts to become an issue when you have lots of devices in a plant, or lots of different, if the plant is very large, right, you don't want to be running mile-long cables, you might just want to have things strung together with Ethernet. The modern incarnation of PLCs is flexible. There's a lot of different things you can do with it, and one great example is this capstone project that I found. So in case you guys haven't seen what PLCs really look like in an industry, this is just a test bed, but it goes to show all the different kinds of things that can be done with a PLC. So there's actually many, many PLCs that are all talking to each other, that are talking to different modules. So here's a PLC here, here's another one, that all go down the chain and talk to each other and handle different things. There's color sensing going on here, there's actuator control, relays that are controlling simple things like moving to the next index for this changer. This is all being coordinated by a few different PLCs that are all in one system, working together in tandem to accomplish a goal. All right, I'm going to go over Arduino a little bit. It's essentially just microcontrollers were a niche that began in the kind of 1990s, early 2010s, or 2000s rather, where computing device control started to become accessible to the hobbyists and to people who didn't need to buy, like this thing's like $300, for example. This one is, I think, like $100, but the license to actually use it is like $2,300 a year. Okay, not exactly easy to get as a consumer, let alone get into and like start learning. This, however, is like $250. You don't need a license, a little bit easier for the educational crowd. This guy is like $8, okay, off Amazon, right? Do very, very similar things. Get cool modules and sensors that can do all sorts of stuff, motors that connect to it. It's kind of like this when I was growing up was my DOS, my basic, my PLC. I learned Arduino when I was a kid. Well, when I was in high school, I'm not that old, or young, I don't know which one. In any case, one thing to be aware of on our PLC is that it kind of is a mini computer. There's lots of different modules that are inside of it. This stuff in particular is not very important, but the next page is. And I'm missing a page. All right. Let me show you guys the software. Let's pop over a little bit. So feel free to log into the computers in front of you. Just hit enter key twice. You don't have to put anything into the password text box. It'll just let you in. So what you guys want to look for is the Arduino PLC IDE. It's actually the second one that comes up. Do not click on the blue one. Click on the black one right here, the PLC IDE. Okay, go ahead and launch that. All right, so this is our IDE, our Integrated Development Environment. For all intents and purposes, this is our blank canvas, the artists that we are, okay? So the other really cool thing is that because PLCs have existed for like 50 odd years. Oh, no good? You might have to move over here just for today if you don't mind. Anyway, since PLCs have existed for 1 million years, there's been a few languages that have come out over that time. The upside is that since this is an educational platform, it supports all of them. So you could work in any language that you chose that have come over the last 50 years: instruction list, function block diagram, ladder diagram, structured text. Sorry, I'm blinking. Where was I going with this? All right, so we can also have any number of programs working in tandem with each other. You can have part of your program working in ladder diagram, part of your program working in function block that's handing off more things to be calculated in structured text. All right, there's actually a lot of incredible power that comes with this IDE that I'll kind of reveal as we go through. But I just wanted to show you guys what this looks like. I'm going to make something that's named Not Quite So Dumb. So I'm just going to go into the top left and I'm going to create new project. Okay, so I'm going to say no. The project is more organizational than anything. This is like, I'm going to sit down and do this thing. That would be the this thing project. If we're going to blink an LED, this will be the blink LED project. My caps lock is on. Blink LED project, okay? Go ahead and connect your PLC to your computer with the included USB cable. You should see like a teal blue cable near you. I might have to find you a cable. Do you have a USB-C cable? I can give you one if not. Okay. So I'm going to lead you guys through connecting to the device for the first time. I'll give you a little bit though to get it connected and powered up. So just the USB-C connection has to be made this time. For the record, the USB-C does power the device. It allows us to upload code to it. It allows lights to blink, right? We have some indicator lights that are useful for us, user controllable and otherwise, but relays will not click, okay? We need 12 volts. We need the PLC to be powered on its terminals for the relays to actually click over, okay? So just keep in mind that we can upload code to it, but if you're trying to get a relay to click and you don't quite know why, it could be that you aren't actually powering your PLC if it's just powered through USB. Okay. All right, so anyone need a little more time? Still working? Okay, so I'll give you a couple more minutes.
What should I do if we don't have a USB-C?
Oh, I got one for you. Here you go.
Am I using this one or this one?
Oh, they're the same. Either one. I gave you two. I don't know why. All right. So just introducing you guys to the IDE a little bit, feel our way around. This is the project kind of navigation tab. This is our main project. Go ahead and create a new project if you'd like. You can call it Blink LED. And once you're in your project, you can double click this tree member, pmain. This is the main program that's running by default. It's always running and it's created automatically with every new program. It's kind of always running in the background. So this program, it's called main, is a structured text program. Structured text being the language at play here, okay? All this program does is it takes a variable called count and it sets it equal to what it is at that current time plus 1. So if count is 0, count will be set to 1. The next loop around, count will be 1, so it says it's a 2, and then keeps doing that, so on and so forth, okay? This count is described here. If I expand global variables on the left, we can see that variable that we just talked about. And we can see different things about it. We can see the name of it. That has to match exactly, by the way. If you make a spelling error for your variable, it won't work. We can see the type that it is. It's an integer, which means that it can hold a number as a data type. It's not just 0 or 1. It could be 0 or 1,000,001, okay? The address we don't really have to worry about. The array we don't really have to worry about. But the initial value is interesting to us because it's when it first comes into existence, right? When it first runs for the first time, we can tell it to start at something if we want to. If it's worthwhile to us that it starts at 10, you can start it at 10, or 0, as in this case. Okay, you can create additional variables in our global variables by right-clicking and doing insert. Okay, and then editing that information is just double-clicking on the name, calling it whatever you want, and going on with your life. There's something in programming called scope, if you guys haven't run into that before. Scope means that variables we put in global variables will be different than local variables, okay? I just clicked again into our main program and we see a window up here called local variables. Okay, local variables, if I were to make one, call it var1, okay? Or even var2. Okay, this variable, var2, can only be seen by this program and this program only. It's a local variable. It's local to this program. If I were to make another program called main2 and I tried to reference var2 inside of it, I would get an error. Yes?
Where do you get to local variables again? I blinked and missed that.
Double click on your main program and it'll be right above it. Oh, it's right here. This is it. So if you right click in here and then insert, yeah. Perfect. So if I had another program like pmain2 and I tried to reference var2 in it, it wouldn't be able to find it, right? Because it's not in main2, it's in main, okay? Global variables, however, do cross program boundaries. If I had many programs and they all needed to know what count was for whatever reason, and count was a global variable, it would be able to find it, okay? If it was a local variable that was outside of that scope, it wouldn't. It would throw an error. What do you mean count? I don't understand, okay? It's specifically looking for what's within the scope of the program. All right, the next thing to introduce is the tasks list. Okay, as you guys might know already, a PLC will run a program over and over and over again, typically, right? We design programs to be run in a loop, so if we're checking a sensor, it'll be checking and rechecking and rechecking all the time, trying to see if that changes, and when it does, it'll do something, right? We can tell the PLC to do that at different rates, and that's what this tasks does, okay? When we first create a program, we assign it to a group. It can be a fast task, slow task, background task, or a init task, okay? So that actually showed up when we first created the project. So main has this already, but if I was to create a new project, for example, new program, you don't have to follow along, I'm just showing you. Create a random thing, it's asking me what task group do I want to assign it to? Do I want it to be in the fast, slow, background, or init task group? If I don't assign it, if I just keep this hyphen here, it'll let you do that, but that could be trouble. Okay, if you do this and create this program, anything you put in here will not run. Okay, it is not scheduled to run. You could have the most beautiful program ever, but it would never actually trigger because you never told it when to. Okay, so assigning that into a group is really important. So as we see here, main is in the fast task group. And we can see here, the period for each of these groups is set differently. So when a program is in the fast task group, every 10 milliseconds, it'll run that program. So count, every 10 milliseconds is increasing by 1, that variable. So 1,000 times a second, right? Or 100 times a second. If we put something in a slow task, that'll run 10 times a second. If we put something in the background task, it'll run once every 5 seconds. That might be like checking in on something that doesn't change very often, running a calculation that doesn't have to be run that often, something that doesn't change at the blink of an eye, right? Init is a special case. Things in here will run only once and when the PLC starts up. It's kind of like the setup function, right? It's I'm alive, yes.
Could you make your own task configuration if you had a specific need?
I would probably change the fast period if you had that specific need, or use a delay. But you could, nothing against it. So the init one is like you apply power to the PLC and what does it do exactly next? And what does it do only once? So that might be like doing a certain thing when it comes up from power, setting things high or low to make sure they're in the right default states, that kind of thing, bookkeeping more or less. Most of the things we'll be doing in this class will be real time, so we'll be almost always putting something in the fast task group, okay? Extremely important, again, for when we're debugging is to make sure that if you create a new program, it's within your fast task group, okay? Because if it's not, like I said, it won't do anything. You'll run it all day and nothing will happen and you'll wonder why. Okay, so if I were to remove that for some reason, I just clicked on it and pressed delete, you can still really easily assign that task, okay? By dragging it into the group just like that. Okay, I'm gonna do that one more time. So main, I'll also drag in that group. Now my program asfast is in there, and so is main. Okay, so both of these programs, this program will be run first, then this program will be run, and that takes as long as it takes. Ideally less than 10 milliseconds, so at the next trigger, it'll start again, right? Okay, so worth reiterating that when we create code, it actually lives on the device. Okay, there's something that we can do called compiling the code. I'm going to delete my last program just so it's compilable. Delete that variable too. Okay, this is the compile button. Okay, when we press this button, and don't press it, it will take a long time to compile. The first time that it compiles, it takes forever because it's creating lots of helper files, thousands of files that are helping us the computer to pull together the computer language needed to actually push programming to the controller. I'm not going to push it because it actually locks out the computer for like a few minutes, so I'm not going to do that, and I can't do anything. But if you were to do that, it would go through its compilation, it would start streaming text through this window down here in the lower left, and it would say something like compilation succeeded or error hit, and then it would list out what happened, hopefully like what the line error was, all that good stuff should show up in this window down here. It should give you a clue if you scroll up a little bit what exactly went wrong with your program. Maybe it was you forgot a semicolon, right? Structured text has to have a semicolon at the end of it. Maybe you misspelled a variable, who knows, right? If something goes wrong, it'll probably print out through here. If nothing goes wrong and we successfully compile, this program is still living on the computer. Okay, after we compile it, it's still in our box or, you know, down here in our machine. It's not on the PLC just yet. In order to actually download it to the PLC, we would first connect to it by pressing connect to target, which we don't need to do. You can if you want to. And then the button next to that, the side-facing arrow near the can, is the one that actually downloads, pushes the code to the device. Okay, that's the critical step, that the code is actually uploaded to here and running on the device. Excellent part about that is it's kind of like burning firmware. Once we program this device, we can pull it off of our computer, we can pull it away from power, and the program will stay on here. It's burned onto this device, right? It's there to stay. Again, I mentioned that because if you hit compile, if you hit our button in the upper left and never actually download the code to the device, nothing won't ever happen, right? You could make changes all day and you never actually see the output of that. You have to actually upload the code to the device. All right, so that's some real simple stuff on the IDE. Let's go over connecting real fast. So the way that you guys should connect is through setup communication. Another critical piece of learning. You guys know how to use the device manager? Pull up a COM port. Yeah? I'm seeing some no's. Okay, so go to your start menu and pull up the device manager. And there's these lovely thing called COM ports, communication ports. Oh, okay, there we go. All right, so you're going to go down here under ports, and this is the life hack. This is the great knowledge. If you want to know what communication port you're talking to, you know, if you have an Arduino or a PLC or whatever, it can assign a random port. It might be number 8, it might be number 9, it might be number 14. It'll show up under this list. It'll show up as 2 different ports for you guys actually, and it's going to be trial and error which one to try when we go to connect to it. It's one of those 2 ports. So I see 1 and 3 up here, but you guys should see more than that, where you see your 2 COM ports. Okay. I want you to mentally note down what COM ports those are, if it's 8 or 9, 10 or 11, 12 or 13. And we're going to try to connect to those ports in this menu. Okay, we're going to click on Modbus, we're going to go to Properties.
Are you open Device Link Manager again?
Online. Yeah, online setup communication. So we go there, we go click on Modbus and then click Properties. And so this, we don't want to change anything else. We want to keep everything the same except for the port. This is where you specify the port to connect to. So it's not 1 or 3, it'll be something else. Okay. You're going to select one of those 2. You're going to click OK. You're going to click OK. And then you're going to try to connect. You go online and connect. If it connects properly, you'll see this part down here that says not connected. It'll turn green and it'll say connected. If it hangs for a minute and doesn't seem to do much of anything, try the other COM port. Okay? Try to connect with the other COM port. Can I get that spare PLC? Thank you.
Neither of mine worked.
Neither of yours worked. Let me see.
Mine did it right.
Just want to double check.
I tried one.
Doesn't seem to be plugged in.
Huh, I plugged it into the computer.
Oh, okay. It's not lighting up. Let's see our device manager again.
Both it shows up in here.
Okay. Okay, 7 and 8. Oh yeah, so these are 7 and 8.
Oh, it's
That's what you
these
should
ones,
try.
that's
Not 1 or 3. Yeah. Yeah. So make sure you guys are doing not COM 1 or 3, whatever else that you guys see on that. Okay. I try to get some parity here. There we go. Okay, so this is more or less what it should look like. Mine shows up as 9 and 10. You might be 8 and 9 or whatever. Okay. So I'm gonna set this up. I'm gonna go online, set up connection, properties, set that to, let's give 10 a try, see if that works. Okay, I know that didn't work, it's hanging, so we're gonna try to, oh, no, I didn't actually click connect. So I'm gonna click connect. Okay, yeah, so that's what it looks like when it's hanging. It doesn't like that, it errored out. I'm gonna change the connection. What's happening? Come on. Dude. There we go. All right, I really wanted to connect. COM9. Connect. Okay. All right, so you'll see upload in progress shortly, but then ideally you should see connect in the lower right. Anyone not see connect on their screen? Anyone not see connect on their screen? No? Okay. All right, so this is, like I said, the button that you would do to download the PLC code, but it already has main on there. Yeah, okay, let's do it. I want everyone to connect and click download PLC code. It says project is not compiled. Do you want to compile? We're going to hit yes. I want us to go through the experience of uploading our first program here. Like I said, this will take some time, and it'll take up to 5 minutes, honestly. It takes a long time. Just the first time, though. Once this is done for the first time, it will be significantly faster for the saved program, because the files can still stay there. There's lots of helper files. Trying to think of other things to go through. Pretty much everything else that I have to teach is downstream of, once we compile this, upload it to the PLC, I'll show you what it's like to actually work with it, to see the code that's on there. So a great, immense strength of PLCs is that they're a black box that we can actually see inside of. Most programs that are written on computers or microcontrollers or Raspberry Pis or whatever, unless you build debugging into them that prints out messages here and there, spits out information about what's going on, it's really hard to see what your program is actually doing beyond like, is it doing the thing that I want it to do? Am I seeing it with my eyes, right? Really simple things like, is a variable a certain number? Is this thing incrementing when it should be? Can be really difficult to suss out if you don't have additional tooling. So what the IDE can give us is a program called Live Debug, which lets us see in real time, like as it's happening, what the current status of each of our variables are. So like this count variable, as we'll see in a second, we'll be able to turn on a mode that will let us see what that variable is at any given second as it's counting up and integrating through. And that's extremely powerful for debugging, for understanding what's going wrong with your program, right? Where your bug in your logic is incredible. And part of the reason why PLCs are so well used, so reliable, so easy, is because it's not just a programmer at a computer with a rubber duck trying to get things to work. You have this incredible IDE, this tooling assistant that can help you figure out what's not quite working, okay? So we're gonna go through, I'll show you what Live Debug looks like. We'll go through a quick practice program on structured text. I'll just show you main again. We'll do a quick ladder logic program, get you guys used to that, throwing symbols down there. And then I'll probably give you guys the rest of today to play around with the program, get used to it, familiar and intimate, okay? Any questions before we do that? I think it's almost done. Yes?
Is the program free?
The program is free, yes. So the program is free, it's free to download. You could do everything with it up to connecting, right? Because you need the actual PLC. But so you can't debug it, but you can make programs in it just fine. You can poke around, all that good stuff. So once it compiled, it said, do you want to restart? I said, yes, I do want to restart. Failed. Downloading PLC application failed. Why did I do that? Okay, so compiled, complete. Download it. Great. Why can't I see my... Live debug mode. Hold on one moment. Technical difficulties. It keeps saying it failed and won't take code. Well, this is as good a time as any to say that this is a new program and it fails in unexpected ways sometimes. So hopefully you guys didn't see this same error that I did, and it will instead, see how I say see no code down here? You guys, after we compile and upload, should say code matches. Okay, that's the state that we want to be in. Yeah.
It says source okay.
Okay, that's where you want to be. Yeah. So, and then you click download, right? Download PLC code. So once you hit download and it prompts you, do you want a cold restart? You say yes. And then the code will then be running on your device. Unfortunately, it's not on mine, so I can't show you. But the next step would be to open up your main file. Okay, go back to your main program, double click on that. So it'll be down here in this window. And then right up here where you see my mouse cursor, you'll see a window that says live debug mode. That will be colorful for you. You'll see a green plus sign underneath my mouse cursor there. And when you click that, you'll see text show up next to our code. Do you guys see that? Right? Super cool. Super powerful stuff.
Live debug mode on this side.
Right underneath your compile button. It's also in live debug mode in the toolbar too. Yeah. So super crazy powerful. This like gives me goosebumps because I've spent so long debugging crazy problems that could so easily be solved for like, what is this variable at this instance in time? So cool, so good. Okay, so that's how we do live debug mode. That's how we download code to the device and how we make a simple structured text program. We're going to do one more program that I'm going to show you guys how to do. All right, so we're going to create a new program. We're going to go add new program. We're going to create a ladder diagram. Okay, ladder diagram is, as you guys may recall, essentially the programming language-ified version of relay logic, which we have coils denoted in brackets, contacts denoted in brackets, and coils denoted in parentheses, and we can wire them together in different ways, right? We can like, add a node and have a parallel output here. We could make this normally closed, all that good stuff is ladder logic and ladder diagram. Okay, so this is just going to be our new program. You can call it whatever you want. The program name doesn't matter. It's just like human readable description for you, knowing what that program does. But we must assign it to the fast task group, right? So make sure that's in the fast task group and then click OK. Just like structured text before, we have local variables up here if we want them, and we have our blank canvas down here. All right, this is our ladder logic, our ladder diagram that's blank. It just has one rung on it. Okay, I had to pull it over pretty far, but you guys see that this is a blank ladder logic, right? That we have one unlabeled coil contact on the left and one unlabeled coil on the right. If I had a variable, if I had some input in one, okay, I would assign it to here like so. Okay, all I did was double click on that guy. That lets you change whether it's negative or positive or normal contact. And then I clicked the name. I typed in exactly in one. If you have a whole bunch of variables and you can't remember the precise spelling, you could totally pull up the object browser, and your variable's right there. Pick from a handy list. Okay. Same deal for the output. If I had like a new variable, call it out1, I could double click on that guy and assign it like so. And now those are bound. Okay. I'm going to show you how to get this into the real world in a second. But this is a working ladder diagram, ladder logic program. All it is saying when input 1 turns on, turn on out 1. Okay? Simple enough. If we wanted to add new rungs to the ladder, you right-click on the ladder, so right-click on this gray region, new network, and then bottom. That adds a new rung down here. You can add as many as you want, as complex a program as you want. Okay. Likewise, we can also click next to the node, just on the line, and then go new objects. Oops, sorry. Yes, sorry, you have to click on the element, and then you can say new contact before, new contact after, new parallel contact, so on. So I'm going to add like a new parallel contact. So bam. We just added a new element to our ladder. We can do the same thing with outputs too. Right-click on that guy, click on coil. We now have a parallel output to our other coil. Just as easy as that. The usual things apply, right? We can like hit delete and it'll go away. We can hit Control Z to bring things back, the undo button. We can hit Control Y to redo. All that stuff is all there. And it really is kind of as simple as that for ladder logic. All right. One more thing, bridging the gap between virtual reality and real reality, right? So how do we, if we set output 1 on, get it to turn on a relay, for example? That's done in our resources tab. So right underneath our project window is a resources tab. Okay. Here is where we assign what does I1 mean? What does relay 2 control? Yada, yada, okay? So starting off, our relay outputs are right here. So I just clicked on that once and it brought up this window. And now we can assign variables to each of our outputs, O1 through O4. O1 being relay 1, O4 being relay 4. So if I were to call this relay 1, okay, this relay, I'm calling relay 1 as a variable. If I was to go back to my new program, look what I'm doing with my cursor, by the way. Our window didn't disappear, it's just in this tab now. Okay, so at the bottom of the screen, right underneath our main window, I went from resources to back to our program. If I change out 1 to relay 1, now whenever something activates this output, it will click on relay 1. Same thing, if something were to deactivate relay 1, if in1, our variable in1 was set to 0, for example, our relay 1 would click off. Okay, that's how that works. We have a couple of inputs on this device. We have a built-in user button. That's this clickable button on the top. It doesn't do anything right now because it's programmable. We have to set it to do something. Let's see what about doing that now. How about? So we go over to our button inputs. There's only one button on this device. Sorry, yeah?
How do we get the local I/O mapping? I must have missed that part.
Oh, resources tab right here next to your projects.
Okay.
Yeah.
I thought differently.
No worries. So we're here in our button inputs. This button is special. Okay, there's only one button on this device. It's literally built into it, so it's got its own section. But if we wanted to use the inputs on the top of the device, if we had a literal button somewhere else or a switch or something we were monitoring, we would use this tab. We would use the programmable inputs. Okay, this is where we assign I1 through I8. Okay, if we had, the 8 different switches from our switch simulator board here going into our 8 different inputs, that's how we assign these variables. Okay, so say I had this first switch hooked in to our device and I put it into I1, I might call that switch 1, right? And then anywhere I put switch 1, if I change in1 to switch 1, now switch 1 controls relay 1. Easy as that. Okay, we're making that association with that ladder diagram. All right, for now I'll give you guys something that'll actually work, that we can test for the first time. We're going to go back to our button inputs. We're going to call this one BUT1, BUT1, our first button. Okay, we're going to go back over to our ladder diagram. We're going to wire in BUT1 to relay 1. Going to get rid of my other ladder logic. So there's just this going on now. So you guys might be able to tell what will happen when we compile and upload this. Whenever we press our user button, our relay would click over. Okay, I want to do one extra thing though. Okay, and I want a LED to also turn on, right? As I want a little bit more user feedback here. So we're going to do something a little bit extra. We're going to go to LED outputs this time. Double click on LED outputs in the resource tab. This is how we get control over all of the LEDs on the device. So there's 4 status LEDs. You see that in the lower left, 1, 2, 3, 4. That's what L1 through 4 do. So if you assign a variable to these and turn that on and off, it'll turn each of these LEDs on and off. It also has an RGB LED on it right next to the user button. Okay, so if you had like an alert that wanted to go off or green for all good, this is where you control that. Okay. Right now we're just going to use L1, which is the light above relay 1. We're going to call that light 1. Okay, I'm going to go back to my program. I'm going to add a new coil, and we're going to call that light 1. Okay, again, fairly simple, but whenever we press button 1, our user button, that will turn on both the relay and the light. So what we should hear is we should hear a click, and then while we're holding down the button, we should see that light 1 stays on for the time that we're doing that. All right, so once you guys have all of that, go ahead and compile and upload, and click the button when you're ready, when it's uploaded, and see if that light turns on. Remember, you won't actually hear the click of the relay until you power it up, so we're just going to see the light blinking right now. Don't worry about the power, the relay clicking, any of that. Yeah. Yeah.
That happened, but I don't have the entire left side of my screen.
Oh yeah, that happens.
Click some resources.
Oh, I would just restart the program, to be honest. Yeah. Yeah, restarts are not unheard of. If you guys have windows that disappear or if it hangs on you, don't be afraid to restart the program. Please save often. Again, this program is new, it's in beta. There might be bugs that we run into.
It says relay 1 not found.
Do you have a spelling error?
No.
Let me see.
Relay 1.
I forgot to say relay the first time. Did you forget to say relay?
Maybe.
So let me see your relay outputs. Oh yeah, you gotta tell it. Yeah. So what I'm saying here is you can put any variable your heart desires. It just has to be the exact same spelling in your program as it is in your resource list. That's all.
Where do we upload we're uploading to this, right? This one?
Yeah. So you can click that button.
This one?
Yes.
Download?
So one more note. If you were worried that your program wouldn't compile, you could click compile. But if you were confident that it would work, you can click download to PLC. It'll automatically compile and then download it for you, so you don't have to do both steps.
I'm way too much fun with this.
Good. So it's working? Excellent. So once it's working, we can work on wiring up power to the device. And I'll lead you through that in just like 30 seconds. I'll give some more people some time. It's working. Anyone else need help? Anyone not able to get? Yeah. Oh no. So it just won't take input?
I found this showed up, and now it won't show any of my project at all.
Oh, so that's back in your project tab?
Right.
And then,
Oh, that's right.
yeah,
Yes. And then
there you go.
this one. Oh, it didn't save it though. Oh, okay. So then I just need to go to
Yeah.
resources and then LED.
Mm-hmm.
And then what do I need?
Whatever you want. It just
Right.
has to match, right?
Yeah, I already named it in here. So which one do I need to name that one? Is it just this one?
Light 1, yeah, because that's your LED.
Right.
Good to go? Yeah. Any other questions? Yeah. How's it going?
We kind of got lost on how to add the ladder logic.
Oh, okay. So go back to your project and then right click your project. So the top level. Yep. And then add new program. And then you just want to click LD for ladder diagram. And then make sure your task is assigned to fast.
Immediately started trying to figure out how to do a left button, and I forgot I have no other button to just.
Yeah, we'll work on the simulator board pretty soon. All right, I'm going to show you guys how to wire this thing next. Okay, so we will need some tools for this. You need a flathead screwdriver, so feel free to come on up and get one when you're ready. They all gone? They appear to be all gone. There's a bunch of tools that are not helpful in here. What the heck? They were in here last semester. There we are, they're at the top. Okay. So we need these for the screw terminal. I'm gonna borrow one just for demonstration. All right, so I'm gonna show you guys how to power this guy. It's really simple. Yes. Yeah, for what it's worth, once we get powering with this, unless you're uploading new code to the device, it does not have to be attached to your PC anymore. It would get power solely from the wall. Okay, so again, the way this works is that this is just a passive component, this barrel jack. So you guys will have a power supply, a 12-volt power supply with you, I believe it is. When we power that in here, it really just has traces that pop the metal from there into this wire, right? So the center pole on your DC power supply, in the middle of the barrel jack, the pin of the barrel, is the positive voltage, so that gets broken out to this wire. And same thing for the ground. These two are connected, okay? This 24 volts is connected to this 24 volts, so if we had to power something else, we could by splitting off another wire, and same with ground, okay? So later on, you're gonna see that we'll have another wire that comes from this one, goes into here to power that as well. All right, a little daisy chain. For now, we're just powering our device. So what you're gonna do is you're going to loosen up the screw terminal just a little bit for one of the positive pluses. Okay, you don't need two, you just need one. Put that guy in there. Oh, yours is already connected? That's okay, you can do whatever you want with that. You can undo it and redo it, you can leave it alone, it's up to you. All right, so at the end of that, you should have something that looks like this, right? As little copper showing as possible. You don't want a lot of the loop coming out in case it shorts against something else. Ideally, you want it more like my black wire is here, so you don't see any copper. It's all within, right? Make sure you can't pull it out. Give it just a little tug, gentle tug. Looks nice and secure. Good stuff. So now, you can go ahead and connect your barrel jack, plug that into the wall into here, and when you press your user button, you should see not only this light up, but you should hear this click. You'll hear a small click from within the device. Sorry? You're missing this guy. Do you have more than one? I don't think that's the right one. I might have to find you one. You got the short end of the stick, I apologize. No? No light? Did you download it? Or did you just compile it?
I compiled it.
So you got to download it as well. So connect to it too?
Oh, that's right. Restart. I got it.
Yeah. We should have another power supply floating around somewhere. Does anyone have an extra power supply in the box? Oh, I see. Here's one. Yeah, I got one. Gotcha. There you go. All right. So once you hear a click and you see a blink, it's mission accomplished. We've done what I wanted to get done today. Okay, I'll come help you. It's all right. All good.
I downloaded it and it worked just fine.
Source okay.
Yep.
Okay, so go to project.
Oh.
Yep. And then open fast. Okay, gaming is in there. That's good. So let me see what we got going on here.
Yeah.
Good. Okay, and then show me what does that map to but one in your resources.
Oh, this one was programmable input.
Aha, so that's looking for an input on here. So
Oh, I just have to flip it.
you want this to be a button input.
Oh,
so
I see.
yeah,
Okay.
I think that'll do it though.
All right. Thank you.
You're welcome. All right, guys, so feel free to play around, implement new logic, mess around with the UI, get comfortable, get familiar. That's it until 6 o'clock. So just 5 more minutes of that and we'll be out. Any questions, let me know. I'm at your disposal. Yeah. What you got? You got it to work?
No, it didn't work.
It didn't work. Okay, let's see what's going on.
So I've got it right here. Right. This one.
So this is,
Maybe do I have to re-download it?
you do, yes. Every time you change code, yeah. I bet you that'll do it. Hey, nice. You're welcome. So yeah, guys, remember you have to download the code. You can't just compile every time it changes. Yes.
So there was a program on this before, and then when I uploaded it, it like wiped it.
Yes. Mhm.
Oh, okay. So it's supposed to do that.
Yes. It gets rewritten every time for this guy.
Okay.
Do you need any more help, or you just keep trucking?
No, that's it.
Okay, cool. So again, a reminder, on Wednesday we're going to have our first lab. We're going to be doing more of this, where I'm going to give you setup to implement, some inputs to work with our switchboard over here, and then it'll just be a lab, a simple protocol. Do the thing, show me that you did it, submit your program online to Blackboard, and that's it, nice and simple. Oh, great time to explain how to do that. Okay, so hey guys, when you go File, Save Project As, this is like you're done with your lab and you're ready to submit it to me on Blackboard, right? You're going to save the project as, you're going to give it a descriptive project name, which is probably your last name, underscore the course. What was that? Oh, thank you, sorry. There we go, that's some more, it's better. All right, so last name underscore ELT140, please. Oh,
Submit this one.
no, not this one. This is just an example, yeah. So this is where it's going. We see this base directory, so by default it's being saved into our documents folder. All right, you're gonna save that. And when you guys go to submit, do not just give me this file. All right, you're gonna wanna try to give me this file and none of the rest of these files, and I'm not gonna accept that as credit. I need these other files with it, all right? So what you're gonna do to do that is you're gonna right-click the folder that was created in our documents, and you're gonna go send to compressed folder. That's gonna zip up all those little files that I need to see your project properly. It's gonna create the zip file, and this is what I want you to submit to me, okay? So I do not want a project folder file. I want a zip containing the entire project. See all that stuff in there? Just to make that clear. Any other questions? All right, we got 1 more minute. Feel free to finish up, pack up. You don't have to clean up. You can keep your PLC on your desk. Just pull the power out of it right? And you can leave it in the box. And that's it for today.
So return the screwdriver.
Please, yes.
See you guys.
Yeah, see you then. See you then. Put it here.